Good morning, good afternoon, good evening to everybody. The Instituto Politécnico Nacional welcomes you to the webinars Terahertz Applications Based on Emergent and High-Performance Electronic Devices, Part 2. These talks are part of the activities regarding Eugenio Méndez Docurro Institutional Chair. These webinars will be held in English. The questions can be sent by using the question and answer chat in the Zoom platform or by using the YouTube chat. Today, there are two changes. Regarding the first talk, this will be given by Dr. Chhandak Mukherjee on behalf of Professor Christelle Manu. The second talk will be given by Dr. Aníbal Pacheco. Chhandak Mukherjee will talk about compact modeling and parameter extraction strategies for IMP double heterojunction bipolar transistors. Chhandak Mukherjee received the Master in Technology and PhD degrees from Indian Institute of Technology, Kharagpur, India, in 2010 and 2013, respectively. From 2013 to 2018, he had been a postdoctoral researcher at the IMS laboratory, University of Bordeux. In the beginning of 2019, he was a scientist at Leibniz Institute for Microelectronics, IHP, Germany. Since October 2019, he has been a full-time researcher with CNRS France, where his research focuses on advanced characterization methods, reliability assessment, and focuses on advanced characterization methods, reliability, and physics-based compact modeling of advanced and emerging semiconductor technologies. He has co-authored over 80 research articles, including 4 book chapters, and has served as a reviewer of various international journals, such as IEEE, TAD, IEEE, TDMR, IEEE, TCAS, Nature, Scientific Reports, Solid State Electronics. Currently, he participates as a work package leader of a H2020 European project for developing 3D integrated computer architectures with embedded neural networks based on vertical nanowire transistors as AI accelerators, and is involved with 2 other French national international projects. Dr. Mukherjee, you have 30 minutes of presentation and 15 minutes for a question and answer session. On your own, please.
Thank you very much. I'll start by sharing my screen. Sorry, yeah. It's visible, right?
It's okay.
Okay. Okay, so first of all, thank you for this opportunity to speak here. And I'll be speaking, of course, as you mentioned, on behalf of Christelle Manu, who was supposed to give this talk. So I will just present some of the interesting outcomes that we have had in the course of our just finished project called Ultimate, which was in collaboration with our French and Swiss partners in the 3.5 Lab, Nokia Bell Labs, as well as ETH Zurich. And this work is entitled Compact Modeling and Parameter Extraction Strategies for 3.5 double heterojunction bipolar transistors. So in particular, this work sheds light on how to extract different parameters of the bipolar transistors and develop the scaling equations based on a physics-based compact model, and therefore use it for circuit simulation and circuit design. So this talk is organized as shown here. I'll start by introducing the overview of the motivation of the work, and therefore explain in detail the extraction flow, how we extracted different parameters based on standard compact models such as HiCom, and how we developed scaling equations, how they were implemented, and different extraction methods at different operating conditions, and with special emphasis on thermal parameter extraction due to the fact that 3.5 technologies suffer a lot from self-heating and mutual thermal coupling. This will be followed by validation of the developed model simulations for 2 bipolar transistor technologies from our partners and 3.5 bipolar transistors, and thereby extrapolating the compact model simulations, extrapolating as in extrapolating the performances of the simulations for other operating conditions and geometries. First of all, for high frequency on wafer TRL measurements, and next for predicting performances of devices to scale dimensions and compare it to the performance of a state-of-the-art. So this brings us the motivation behind this work, which is the recent increasing interest in the optoelectronic integrated circuits, and thereby the convergence of technological convergence between photonics and electronics. So the principal idea behind this is to incorporate this photonic and the electronic components in the same chip, in the same die, on the same substrate, that is the indium phosphide substrate, including devices such as HBTs, bipolar transistors, used in electronic circuits such as amplifiers, as well as photodiodes such as unitraveling area photodiodes, which can be used for photo detection, optical generation, etc. So the application targeted, to keep in mind, is for beyond 5G communication circuits, and they are naturally being forced to operate at terahertz frequencies. So in those frequencies, naturally, there are higher losses. So it has to be taken into account the interconnect distances and the delays that come in play, as well as the parasitic contributions at higher frequencies. So the interconnects are no longer resistive connectors. So there are a lot of challenges to overcome. Even though the principle exists of this integrated circuit, which is monolithically integrated on the indium phosphide substrate, in order to minimize the losses in the chip, intra-chip, as much as possible. So the first of all, the main challenge is the optimization in terms of the epitaxy, first of all, because the 3.5 heterojunction bipolar transistors are still evolving. We can call them as an advanced technology, but not as industrial standard as the silicon bipolar transistors. And thereby it has evolved already through many generations, which began with the type 1 heterojunctions, where narrow bandgap gallium indium arsenide was used for the base, and the collector was made of indium phosphide, and thereby creating blocking layer between the base and the collector. There were blocking carriers at higher current densities. So this was overcome by grading the composition of the base gradually from low, narrow to higher band gaps, and thereby easing the transitions. And then came the type 2 heterostructures, which was gallium indium arsenide antimonide incorporated into the base. So we have taken both the technologies for these studies in this project, but there are other aspects to be taken into account for designing such optoelectronic integrated circuits. So as I mentioned, the first one is to model interconnects at high frequencies, also the reliability constraint, which is due to the self-heating and the heat dissipation in the photodiodes, as well as the transistors. But there is also a requirement of multi-physics simulations since we are dealing with both optics and electronics at the same time. So it is necessary that we have a common tool for both of them, and ideally a SPICE simulation platform. And thereby we come to compact models, which are basically the bridge between the process and the design, acts as an intermediary. So it can be incorporated in what we call the process design kit, along with the information on the technology, as well as the layout information. So in order to develop such extraction strategies, the design flow that are conventionally used, it looks like this. So the compact model that contains the model equations that is used along with a set of model library that contains a set of model parameters that takes into account scaling rules. And why do we need scaling rules? Because we need to make the model predictive. So this is one of the most important reasons for having a scalable as well as physics-based modeling approach. So the scaling rules can be designed based on the device information, such as the geometry and certain transistor configurations, fed with the information of the technology itself, as well as a set of model parameters. So the fundamentally, what is done is that these parameters are extracted from a single geometry, and thereby the scaling rules are generated by the foundry itself for each of the local parameters, and which can be incorporated in this scaling library and used along with the model equations in the compact model for circuit simulation and design of electronic circuits. So the model parameter extraction flow, whether it's scalable or not, follows a certain set of steps which are common and which can be the same for all bipolar transistor technologies, which begins with the initialization of the technological parameters that I mentioned before, which are pertinent to the technology itself and the device geometry informations. But then we have to extract certain parameters related to the extrinsic devices before we extract parameters related to the intrinsic one. These include the series resistances, oxide parasitic capacitances, as well as their junction capacitances at the base and the collectors. And this is followed by extraction of model parameters at low to medium injection condition for the base and the collector current, as well as the temperature related parameters and the thermal impedances, the resistance and the capacitances. This is followed by extraction of parameters at higher frequencies, which is done by using S parameters up to high frequency, and extract the parameters such as the transit time and its bias dependencies. So this flow is separated into these segments because of the fact that there is a high degree of dependency between these parameters. So we have to have a certain degree of confidence in the parameters that we extract. This is why we have to proceed systematically, and therefore parameter extraction flow has to be well defined. So we have adopted similar parameter extraction flow for our work as well. It has to be kept in mind that the direct parameter extraction method is always more preferable because it is based on a certain set of measurements for extracting a certain set of parameters related to a certain operating conditions. But there are certain limitations of this approach because of the sometimes unavailability of the structures, or that the fact that these extractions do not describe the device performance under all operating conditions. So this is what we call local extraction, but there can be a global extraction flow method, or which we call a global optimization strategies. So the optimization strategy is basically a computer algorithm that optimizes all parameters of the devices, that describes the device operation under all operating conditions. And this can well describe the performance under all operating conditions. But the fact is that this is an optimization. Sometimes it can deviate from the real range of these parameters. So the ideal approach is to adopt a parameter extraction strategy, which is hybrid in nature, that makes the best of both the strategies. So local parameter extraction wherever it is possible, and therefore optimizing using a global algorithm for generating the set of device parameters, which can be optimized to remain within the physical limits of the parameter in question. So the compact model that we have used for this study for bipolar transistors is well-known model, which is HICAM model. The HICAM is a physics-based model, which has a strong physical basis, and it captures well the dynamic behavior of the circuit of the bipolar transistors. But what is more important is that the model formulation is charge-based and thereby separates the contributions of the different regions of the transistors that are not only limited to the intrinsic device, but also the external base collector and the base emitter peripheral regions, as well as the substrate network. So this separation of the charge contributions makes it easier for generating the scaling equations for the transistors. But on the other hand, there are more than 60 parameters for the 2D transistors in HICAM model. Therefore, the parameter extraction strategy is very complex. And you have to keep in mind that there is a strong correlation between the parameters and the different operating conditions. So a systematic extraction of certain parameters at different operating conditions have to be followed. And thereby we can generate the scaling rules associated with each local parameter. So this is the complete equivalent circuit of the HICAM model. As you can see, how the intrinsic transistor as well as the extrinsic contributions are taken into account. But it also recalculates the junction temperatures dynamically using a thermal network for describing thermal resistance of the bipolar transistors, as well as takes into account the noise correlation and non-quasi-static effects. But what has to be kept in mind that HICAM inherently is not scalable. It supports scaling, but it's not scalable inherently. Unlike the standard MOS models, where the scaling equations are incorporated within the model itself. None of the bipolar transistor models, such as SPICE, Kamelpoon, Rybik, HICAM, Mextrum, they don't have scaling rules within the compact model itself, but it is generated or designed by the founder itself or the user itself. So the scaling library has to be developed based on the monogeometry parameter of the transistors, and thereby each local parameter needs to have a set of scaling rules, a scaling strategy. As an example, here I have shown how one parameter can be represented as by two separate contributions from the intrinsic and the peripheral device. So the total junction capacitance is expressed the sum of the intrinsic contribution, where CJA is the intrinsic parameter, it's physics-based model parameter, and CJP is the extrinsic contribution. So area and perimeter are also two parameters related to the device geometry. So if we do some sort of mathematical manipulation, we arrive at this equation, and we can easily extract these two parameters of interest just by extrapolating from the graph. So if we plot on the y-axis the normalized junction capacitance as a function of this parameter, perimeter to emitter area ratio, we get these straight lines, and from the slope we can get the perimeter contribution, whereas the intercept gives us the intrinsic contribution of this capacitance. So this can be done for all parameters such as the currents, capacitance, and we can visualize this concept as a representation of the total current by two transistors in parallel, each of them representing either the intrinsic or the perimeter contributions. Whereas this is the total emitter area, which is divided into the intrinsic and the perimetric contributions. This can be further extended and generalized, where more refinement can be done for the perimetric contributions, where the intrinsic contribution is already there. And the perimetric contributions can be divided into three other parts related to the width, the length, and the corners. And thereby we can imagine 4 transistors in parallel. Each of them represents a contribution of the parameter in question. So before we proceed with the parameter extraction, some of the technological parameters are to be pre-calculated and entered into the simulator, which are, for example, zero bias hold charge, area and the perimeter dimensions of the devices, and the design rules, for of course. So once we have done that, we have the different steps that I have already mentioned to follow. First of all, we begin by extraction of the junction capacitance, the base emitter junction capacitance. Here, the table summarizes the total geometries, the number of geometries that were available for characterization, with different emitter lengths and different emitter widths for each of the emitter lengths for both the indium gallium arsenide on indium phosphide bipolar transistors, as well as the gallium arsenide in antimonide indium phosphide bipolar transistors. So the idea is to extract the parameters related to the low injection operation first. For this, the first step is the extraction of the junction capacitance, which can be extracted from the cold S parameter measurement, which is where we allow negligible current through the junction, and therefore sweep the bias across the base emitter junction and extract the base emitter capacitance. So these parameters can be extracted from the de-embedded Y parameters. And thereby we can separate the intrinsic and the peripheral contributions, as I mentioned before, and showed in the graphical extraction method. So this has been done for both the technologies. And as you see that these scaling equations already defined are quite agreement with the measurements. Explicitly, we can see how the base emitter capacitance can be plotted as a function of the width and the length of the two technologies, and it shows also a good scaling. The same thing can be done for the base collector capacitance using the same coldest parameter measurements, for this time for the base collector junction, and it again follows the same procedure as separating the intrinsic and the peripheral contributions. Here you have to keep in mind that these extractions were also optimized after the first set of parameters, first guesses were derived. We ran an optimization combining all the characteristics that were measured. So both for the bipolar transistor technologies, good scaling for the base collector junction have been observed. The next parameter in question is the extraction of the parameters related to collector current at low to medium injection again. So we begin by extracting the parameters at zero base collector voltage, so that the effect of the base collector junction is minimized, and using the same type of scaling rule. So in both cases, what we plot is the normalized collector current with normalized by the exponential VBE by VT, so which is just a representation of the saturation current, and as a function of the base emitter voltage. In both cases, the parameters extracted show good agreement, and the model parameter set show good agreement in the simulation against the measurements that we have done. Similarly, here explicitly, the collector current is plotted as a function of the emitter length for both technologies. And finally, this shows all the geometries that we characterized, the Gammel plots, the forward Gammel plots for all the geometries that we characterized, showing the collector and the base current. The next step is the extraction of the transit time. The first step is again to extract the contribution of different parameters at zero base collector voltage in order to minimize the impact of the base collector junction. So here you see the classic equation where the transit time is represented by the cutoff frequency, the base emitter and the base collector capacitances, and the transconductance, as well as the parasitic extrinsic collector and the emitter resistances. So here, in collaboration with ETH Zurich, we also performed a ticket simulation of the devices of the two technologies. And there are some certain discrepancies between these results due to the fact that these extrinsic contributions were not taken into account in the ticket simulation, whereas the HICA model takes them into account in the parameter extraction flow. So when we had the chance, we subtracted these contributions from the HiCAM simulation and compared them with the TCAT simulation, and observed that there was good agreement again between the TCAT and the compact model simulation. This again confirms the fact that the intrinsic parameters are extracted quite accurately. And finally, this is the bias dependence of the transit time at high current densities. Sorry, this is for the zero collector-based bias again, but we did the same for different values of the collector-based bias, which was verified from the cutoff frequencies Ft and Fmax. So at first, they were optimized again after all these previous parameters were extracted at low to medium current at VBC 0. And this takes into account the verification of the parameters for the zero bias transit time, base collector junction capacitance, and parameters that describe the dependency on the base collector bias. At high current densities, the excess transit time, the increase of the excess transit time, is modeled through high current parameters in the HiCAM model. So in both cases, you can see that the Ft and the Fmax as a function of the different collector bias are quite well described by the HiCAM model for both the technologies. In addition, we extracted the temperature related parameters, because all these previous extractions that I've shown were for room temperature measurements. But this is also important that we extracted the temperature related parameters due to the fact that the thermal management is important for these bipolar transistors. And these were also extracted, shown here, shows good accuracy of the model for the different temperatures that we used for the measurements, -40, 0, 25, and 35 degrees centigrade for both the technologies again. As a final validation, we simulated the output characteristics as a function of the base emitter voltage as well as the base current. In both cases, this validates the model parameters set that we have extracted. A special emphasis was given to the extraction of the thermal parameters, because a single pole RC network that describes the thermal impedance of the bipolar transistors in HiCAM model was not sufficient to describe the behavior of these 3-5 bipolar transistors under different operating temperatures. So what we did was that we extracted the RTH values from preliminary extraction methods, such as one which is called intersection method. But we also used low frequency S parameter measurements for extracting the thermal contributions. So for this, we developed a scalable model again for the thermal impedance, considering two different heat diffusion scenarios throughout the transistor. And therefore, we extracted the thermal resistance from the low frequency S parameter measurements performed in the 300 kilo to 3 gigahertz range, and extracted the thermal impedance. So this was validated also against the measurements and shows good accuracy over all the geometries that we studied. So finally, once we have a certain degree of confidence in the parameter set that we have extracted, we have validated the model simulation against measurements at higher frequencies. So for this, the measurements that were performed used on-wafer TRL calibration, because of the fact we wanted to calibrate under the same substrate and not use standard salt calibration. So the TRL calibration yielded good frequency response for both transistors, and these transistors were biased at peak FT conditions, but you can still see some oscillation despite the TRL calibration at higher frequencies. But these measurements were performed on wafer till 500 gigahertz for both the technologies. Here, the set of results were not available at the time for this, but they were performed nonetheless. But we do observe good band continuity over the different frequency ranges, and HiCAM simulation was used to describe these performances, the same model card that we extracted before. So the model shows good agreement again, and thereby highlights the fact that it has good predicting capability because of the fact that it is the scaling as well as the physics-based nature of the model. Then we further exploited this predictive capability for predicting the performances of transistors at scaled nodes, particularly for predicting the certain figures of merit of this related to these 3.5 technologies, such as the FT, the current gain, the Fmax, and the thermal resistance. So the predictive results suggest that there's an improvement predicted over the state of the art of the same dimension, as you see here. And the current gain is more or less stable for both technologies, but it also shows higher thermal resistances. On the other hand, as area is scaled down, the junction temperature is reduced. So it kind of compensates the increase of the thermal resistance as such scale dimensions. So what we fundamentally did for this is that we use the same model card that we extracted, and without modifying any of the epitaxial features, we extrapolated the performances just by changing the dimensions in the model card. And therefore, we could, with a certain degree of confidence, predict the performances of these scaled nodes. So this could be very helpful because of the physics-based scalable modeling framework that we put in place here. And the next steps would be to further optimize this process with the help of this scalable model formulation. So that brings the end of the talk. Thank you for your attention.
Thank you so much, Chhandak, for this pretty interesting talk about 3.5 heterojunction bipolar transistors. Now we will begin with the questions. First of all, Eduardo Lugo, congrats for your excellent presentation, Chhandak. And the question is still missing, but yes. Did you simulate your devices only in 1D modeling or 2D or 3D?
Not in 3D, but it's the HiCAM model was for 2D transistors. So yes, 2D lateral effects were also taken into account, not only just the vertical.
Okay, perfect. Thank you. Yes, there is a question from Aníbal Pacheco. HiCAM has been developed for silicon germanium heterojunction bipolar transistors originally.
Yes.
What kind of improvements do you need to apply in order to consider 3.5 devices?
Well, as such, we use the same model without modifying anything. So this again shows that HiCAM is also applicable for 3.5 transistors. Maybe there would be some specific process-related improvements, but so far, in terms of the organization of the model, I think it describes quite well 3.5 transistors as well. So far, we have seen for 3 generations of these technologies that we have studied during this project. So HiCAM has worked quite well for the 3.5 transistors.
Thank you for your answer. Yes. There is another question from Reidezel Torres. Thank you for the presentation. What range is considered low frequency during the parameter extractions, and what effects are accentuated at these frequencies to make the corresponding S parameters relevant?
Are you talking about this one? Because this is the low frequency S parameters that we have used. For other measurements, we used the frequency range between 250 megahertz to 40 gigahertz for all extractions, except for thermal extraction, where we used 300 kilohertz to 3 gigahertz. You mean this low frequency range?
I think so. Okay. Yes, that's the slide.
Yeah, because we used this low frequency S parameter measurements because from the Y parameters we could extract the dynamic self-heating of the transistors, which is not just the static part. So from this, where you can see the frequency goes to lower frequencies, it can be almost assumed to be constant, which gives the value of the thermal resistance, not the impedance. But there are the different layers which contributes to the capacitance of the thermal capacitance of different layers of the transistors. So this gives us this frequency dependence in the low frequency S parameters. But we saw that using just one RC network, one pole network, it was not enough of for describing the entire behavior. So we had to use 3 different regions based on the geometry. So it has to be adapted on the technology.
Okay. Thank you so much. I have a couple of questions regarding slides 5 and 6. First of all, slide 5, please.
Yes.
Yes. Here there is a flow diagram.
Mm-hmm.
And my question here is, what about the intrinsic base resistance? Does this parameter is extracted using a modeling approach or is modeled?
I mean, this is modeled, I would say, because honestly, these test structures were not available for extracting these resistances. It would be ideal to extract based on set of specific test structures for these technologies. So we had to, as I mentioned, there is the optimization method. So we were pretty much doing that. So we started by extracting the low to medium injection parameters, and therefore we went on optimizing the other parameters. So yes, in a sense that it was modeling or optimization rather than extraction directly.
Okay, thank you. There is another question. This is regarding the in slide 6, please. There is an intrinsic part of the device, and there is, of course, the extrinsic part, mainly at the base collector junction. What about with the base collector distribution factor, X? This parameter splits the intrinsic and extrinsic base collector capacitance and the intrinsic and extrinsic base resistance. In this model, HICOM, this parameter is considered, it is neglected.
No. What you mean is it that the base extrinsic resistance and intrinsic resistance are considered separately? This is what you mean? In the HICOM model, yes. But we also have scaling rules for this. I mean, the scaling for the extrinsic base resistance and the collector resistances. So this was, again, I mean, the generalized approach that I mentioned in, I think, a couple of slides down here. So this was done for all these parameters.
Okay. I understand. Yes, of course. And finally, my last question. There is a high frequency noise model in this HICOM model that you have developed. What about
high frequency noise model, you mean, or measurements? This slide
modeling.
No, we haven't done as such any high frequency noise modeling for these technologies.
Okay. Thank you. There is a last question from Dr. Luis Manuel Rodriguez. Is this HPT repeatable in fabrication? This is
Yes.
an auto-aligned architecture process?
If you're talking about the variability or process dispersion, yes, to some extent. I mean, we worked with both industrial and academic technologies, but of course, they don't have as high yield as the silicon transistors. That is normal because this is still considered as an advanced technology. But we obviously did see better stability or yield for the 3,5 lab indium gallium arsenide indium phosphide HBDs, because the process is more industrialized, where these technologies are more academic. But yes, I mean, we have chosen the representative device, I would say, for these technologies for extraction, so which represents the entire technological generation, I would say. But there are process dispersion variability in these technologies higher than the other one.
Oh, okay.
There are some, yes.
Thank you. Well, the other question is similar as mine. So we have already finished with this question and answer session. Thank you so much. I will share my screen to read your diploma.
Thank you. I will stop sharing now.
Yes, please. Thank you.
Thank you.
And yes, sit. Yeah. Well. Share screen, yes. Instituto Politécnico Nacional and the Eugenio Méndez Docurro chair present this certificate of participation to Chhandak Mukherjee for his participation on the webinar, Terahertz applications based on emergent and high performance electronic devices part 2, with the conference compact modeling and parameter extraction strategies for IMP double heterojunction bipolar transistor. Thank you so much, Chhandak.
Thank you very much. Really appreciate it.
Thanks. Well, just give me a second, Aníbal. I'll be right back. Okay, I'm ready. I'm sorry for the delay. We have
No
a couple
problem.
of minutes. Our next talk is presented by Aníbal Pacheco-Sánchez from Universitat Autònoma de Barcelona, Barcelona, Spain. And this talk is called The Importance of Being Compact, Modeling Two-Dimensional Devices Towards RF Applications. Aníbal Pacheco received the Doctor Engineer degree in Electrical and Computer Engineering from the Technische Universität Dresden, Germany in 2019, and Master in Science degree in Telecommunications Engineering and Bachelor in Engineering degree in Electronics and Telecommunications from the National Polytechnic Institute, Mexico, in 2011 and 2008, respectively. Nowadays, he works as a postdoctoral researcher at Universitat Autònoma de Barcelona, Spain. Dr. Pacheco has supervised undergrad and grad student theses in Germany, Spain, and Mexico. He serves as a reviewer for several scientific journals, and he is currently involved in projects within the GraphCat, the graphene community of Catalonia, as well as within the graphene flagship from the European Union. His present research interests involve the characterization, parameter extraction, compact and numerical modeling for emerging transistor, diodes, and switches technologies towards the development of RF applications. Dr. Pacheco, you have 30 minutes to present your talk, and then we will have the question and answer sessions. On your own.
Perfect. Thank you. Let me, okay. Perfect. Thank you, Eloy. Let me do this. Okay. Yeah. First of all, well, I changed a little bit the title. Yeah. So I can cover other topics as well. And yeah, I would like to start by saying thank you to all the organization, including Eloy Ramírez and also Miguel Sánchez. It's the third year in a row that I'm participating in this colloquium, and I'm really glad to be here. So, I don't know how to well, okay. First of all, yeah, as Eloy said, I work in Barcelona right now, which is in this part of Europe. And I work in the Universitat Autònoma de Barcelona, where we have a lot of green areas. And specifically, we work in this building, the engineering building, in which the electronics engineering department is included. And inside it, we have a small group in the computational and electronics research group led by Professor David Jimenez. And currently we work 4 different researchers, Pedro Feijó, Ferni Chavez, Nicolás Mavredakis, and myself. And also Fran Pasadas, he has been an active member of our group. Now he's with Universitat de Granada. But I'm also include him here, so because I'm also presenting some of the work he's doing, or he has done in our group. Okay. Well, let's start first by. I'm sorry, Eloy, can you help me to hide this part here? I am
yes, of course,
familiar with this.
Can you click on the, it's okay. Now it's okay.
You can, it's okay. I mean, the title is not seen, but okay. No problem. I can continue here. So the general motivation for this talk, so it's to give a more general overview of compact modeling. So the last talk given by Chhandak, it was like really interesting. And it's a good example that compact modeling is already considered in advanced technologies, but compact and numerical modeling sometimes is overlooked when we're talking about emerging technologies. In emerging technologies such as 1D or 2D devices, so transistors or any electronic devices based on, for example, graphene, carbon nanotubes, 2D materials, etc., we have 2 different approaches mainly. The first one is the proof of concept devices, in which there is a group which fabricate devices, then they get it, and they show some results, and that's it. And the best case scenario, sometimes the fabrication group, they develop the device, they fabricate, they measure it, and somehow they build circuits with it. And there, inside this approach, also, in some cases, they directly fabricate circuits without analyzing the device before. And what about if we want to reproduce these circuits? So that's the question. and how reliable is this process. Then the third approach that I would like to share with you is a collaborative framework in which all the three different steps are correlated, so you can you have a direct communication between the different groups, and you cannot build only one circuit, but maybe integrated circuits with emerging technologies. So my goal is to share with you my view that a more holistic approach is usually missing in emerging technologies, and we should fill that gap. So I'm giving you several examples, or some examples of compact modeling and how useful it would be if we consider that in order to boost the performance of different devices. So this is the outline, but okay, I'm not reading it because we are going step by step. First, let's start with device modeling purposes. Why do we need to model a device? So, for example, let me start with an analogy with food. We all love food. Yeah, so you have the raw materials as lettuce, cheese, tomato, bread, or whatever, and you can combine them in any way you want. So if you combine them properly, you get a device, which is called a sandwich. So in the sandwich, we have all the raw materials combined together, and we know that the bread should be on the sides of the sandwich so that you don't lose your lettuce or so. And then if you combine this device, this sandwich, with other devices, you can have an application. I mean, our application is this breakfast that I show you here. So basically, the question is, we give this for granted, yeah, but have you ever wondered how was the first sandwich prepared? How it was reproduced? So how was it scaled? How was combined with other devices for breakfasts? So there are two different approaches to get this done. The first approach is to try and error. So it's an empirical approach. So you try first the bread, for example, the lettuce on the sides of the sandwich, then the tomato, for example, you see that it doesn't work, and then you put the bread, okay, and then you say, yeah, well, that's working, then I would prepare more sandwiches. Or you can also solve formulas, so in this case, chemical formulas, and you can see that the bread is more dense than the lettuce, and they can hold all your ingredients together, and so on. In both cases, you need a recipe, and that's why you need models. In electronic devices, now coming back to our area, you have materials as this carbon nanotube here, you have a device as this transistor that you have in the middle, and then you have an application. Here, for example, as this RF amplifier made out of carbon nanotube transistors. But you need a recipe, you need a model to go from the material to an application, and also from the device to an application. You need to consider everything, and this bridge is the compact model. Of course, it cannot work alone. You need a collaborative research framework between the technology platform, providing the materials, and building the devices. The device modeling engineers, which translate the physics into an engineering language, and of course the circuit designers. The circuit designers are in charge of bringing the device into applications, and lately to integrated circuits. You need this collaboration for any successful electronics technology. There is a constant feedback between these two groups, the technology platform, device modeling, and circuit design. As I said, this is granted in advanced or incumbent technologies, but sometimes it's really missing in emerging technologies. That's why I'm showing again and again this slide, because I think it's really important to work together, not as a competition, but to work together with the technology platform, with the device modeling group, and with circuit design. We need feedback all the time in order to achieve a reliable and reproducible device technology for any application. For example, analog or RF application, which is the case we are studying right now. Now, let's see the different device modeling approaches and when and why we're using them. First of all, you have the atomistic simulation, the atomistic modeling approach. It consists of quantic simulations. And basically what they do is they model atom by atom of a particular region in the transistors. In this case, for example, in the left-hand side, I'm showing a metal contact and a carbon nanotube. So basically they build matrices with it, and then they solve some equations by using density functional theory or non-equilibrium Green's functions, and they can provide really important information. So for example, here in the central figure, we see electronic bands of a carbon nanotube in the middle, contacted in the two sides by different metals, gold, aluminum, chrome, copper, nickel, and so on. In this case, by observing these simulations, you can easily see the type of transport that it's going to be dominating in your device. But again, this is for a short region. Why? Because it takes a lot of computational burden to simulate this and a lot of time for it. So it's intended only for short devices or really small regions of your transistor. It gives you information about precise phenomena, and it is really useful to understand what's happening in these small regions. And also, it can be used as a support for other models calibration. The next approach would be the numerical device simulation approach, in which you provide a self-consistent solution of the Poisson equation with any transport equation, the diffusion, Schrödinger equation, Boltzmann, etc. The computational burden of this equation is variable because, and then the simulation time is also variable, because then you can have not only one small region of your device, but a whole transistor, as the one shown here, which is a CNT-FET, in which all the device is simulated here, and it can go from a small device or a small channel device to a large channel device, and it can provide you important information such as the transfer electrical characteristics for different channel lengths, as shown in the middle, and also it can provide the electronic bands for your device, in which you can see if you have, for example, short channel effects, band-to-band tunneling, etc. So it gives important information, and it can be used as a support for compact modeling and also to provide performance projections. But the main character of this presentation is the compact modeling approach. And here I'm just giving you a general overview. So basically, in a compact model, you have intrinsic and extrinsic device phenomena, which is represented by lumped elements associated with equations that are valid for several different conditions. So, for example, you will have a total equivalent circuit represented in the different device phenomena, and each of these elements are defined by equations. For example, here I'm showing one equation for the current source of this equivalent circuit for a carbon nanotube transistor, in which you see that it is many algebraic equations. Because of this, the simulation time is short and it only consumes minimum computational burden. You can use this kind of compact models for circuit designs. This is the language the circuit designers need in order to build applications. Well, another important aspect of the compact model is the parameter extraction, as it was also covered in the last talk, in the previous talk. I will go deeply into each of these topics later. So how do we define a compact model? In this graph, I'm sharing with you, we have in the y-axis the complexity of the models, and the x-axis the physical basis of models. The atomistic simulations is a more complex in terms of computational resources, and because the physical basis is stronger than the other ones. Yeah, and as I said, it's useful, but for small regions and for specific phenomena. In the other part of this graph, we have the table and fitting models. So the computational complexity is like really, really low, and the physical basis is also low. And these models are useful for a quick and immediate characterization in the lab, for example. In the middle part, there's the two approaches that we are mainly used in our group. We have numerical device simulations that I talked to you before, I mentioned before, and we have physics-based compact models. As you see, I mean, they are not as complex as the atomistic simulation, but they are more physics-based than just fitting models. And a practical material device circuit co-design approach is only possible with compact models. Yeah, if you want to build a circuit out of carbon nanotubes, out of graphene or whatever, you will need a compact model always. Why? We have here, for example, a device, a graphene-fed device, in which we have selected an intrinsic region just below the gate. So this is the region of interest. We develop a compact model for it, in this case, a charge-based approach, which accurately describes the device performance. So all the charge inside this device is captured by these capacitors that are here, the charge inside the channel, the charge in the top gate, and charge in the back gate, etc. So, and each of these capacitors are associated to equations, but this is the language circuit designers need in order to build applications. Once you have this compact model well defined, you create a symbol in the symbol of a transistor, which is your intrinsic device, and then the compact model engineer smoothly translates the physics of the device into engineering language, which is a transistor symbol, a resistance symbol that we have all seen when we are playing with circuit design software, for example. With these symbols, then you can build circuits. In this case, for example, there was an RF balloon, so an important part of a transceiver made out of GFETs. And basically, by just translating the physics into an engineering language, you can create or design circuits and then fabricate, give the performance projection of it, and so on. It's strictly, the compact model is strictly required for applications. The definition of a compact model, there are several in the literature. I'm just reading here mine. You can agree with it, you cannot, no problem. If you have a better definition, I define a compact model as an accurate representation in an engineering language of physical phenomena within a device in order to develop applications with it. Yeah, it is quite simple, and it's a summary of all the things I have said before. Now, just to give you an example of industrially suitable physics-based compact model, which is in line with what Chhandak presented before, actually. But I want to mention briefly, like all the features that an industrially suitable compact model requires. So basically, each model element should be associated with a function, including parameters of current, of temperature, of geometry, etc. Yeah, a compact model can help the process development since it includes all the physical effects. It can be helped for debugging process issues. So it can actually save money for the industry if you have a well built compact model. So you need a parameter extraction, so like a well-defined parameter extraction, such as the one presented in the last talk. So I'm not going in detail into this, but you need to build your compact model in a way that a simulator or a circuit design software can read it. It needs to have an equivalent circuit topology and equations that are continuous and differentiable over different conditions. And another important point is that the compact model should be modular and it should be easily extendable. And as I said, for the circuit designers, the compact model should be easy to understand. In the best case scenario, it should be a black box. They shouldn't care about it. They just need to focus on build these awesome applications that we are using every day. As for example, all the RF transceivers that we use every day in our phones. This is just an example. I just wanted to give you an example, but I mean, this was presented by Chhandak before. This is the Haiku model. It was developed originally for high-speed silicon germanium HPTs, such as the one I'm presenting here. And it consists of all these equivalent circuit, including also the external thermal network, NQS effect, vertical for the input and for the output. And each of the parameters inside this equivalent circuit is associated to an equation which describes a physical phenomena. And here I'm just showing you a validation of the compact model in terms of the transit frequency over the current density. And you can see that this compact model, for example, works for the gigahertz range already. Now, let's go to the emerging devices, modeling emerging devices towards RF applications. The first example would be a carbon nanotube field effect transistor. So in my former group, we developed a large signal compact CNT-FET model. The name is SICAM. I present you here the equivalent circuit. The intrinsic part is illuminated in red and in blue. And basically here, when this compact model was developed, there was a problem in the CNT-FET technology that you have a lot of undesired metallic tubes. These metallic tubes are included in the blue part of the intrinsic compact model. And nowadays, the technology has been improved and the metallic tubes numbers has been reduced at the point in which this part should not be considered. And that's one of the importance of being modular. So for example, at this stage of the technology, our compact model can still work because if you just eliminate this part, you can still work with the other part, with the intrinsic part for the semiconductor devices and extrinsic parasitic network, associated all of them with different equations that, as I said, it doesn't include, they don't include, sorry, derivative, integrals or a lot of derivatives, because they need to be continuous. So there is no problem when the circuit design simulation software is solving these equations. So of course, we have verified the model experimentally. Here we show the FT and Fmax over different VGS. The model is in line, represented with lines, the experimental data with symbols, and we have validated this by with different PDS. So it was validated over a wide bias range. And however, there have been some technology improvements since we started with this compact model. Nowadays, as Martin Hartmann presented yesterday, there are CNT-FET technologies which are close to RF CMOS and are getting closer and closer to the performance of 3.5 HEMT devices. So we need a continuous model improvement at the same time as technology improvements. Basically, the most recent improvement of this compact model was presented a couple of months back, and it included an improvement in the charge definition. By adding this improvement, you can see here that the transit frequency, the cutoff frequency, is better described by the new version of the model than the previous one. Yeah, so you don't just need to provide a compact model, you need to maintain it and improve it. So since the technology is advancing, as here Rutherglen said, it could ultimately offer both the high performance of HEMTs and integration compatibility with CMOS. And it is also valid for graphene transistor that we are going to see later. For these next generation CNT-FET-based applications, we require compact models. Otherwise, we are not going anywhere. When you have these compact models, you can have also performance projections at a circuit level. In this case, for example, we use the compact model, experimentally calibrated, to build the first proposal of FSK and PSK modulators based on CNT-FETs. If you have accurate, versatile, and smooth device model, you can build complex large-scale circuits. I'm not going into the details of it. If you want more details, you can check it here in this publication, or for the people in CIME, I will talk about it at the next conference, and the conference next week, the CENIES conference. I will talk about this time, but my message is that if you have an accurate model, you can build complex and large-scale circuits. Let's go now to graphene field effect transistors. So, as a proof of concept devices, the GFETs can provide an extrinsic cutoff frequency of 10 gigahertz. Yeah, so they are suitable, or 10 or higher gigahertz, even till 50 or 60 extrinsic FTs. So they are attractive for analog and RF applications. So you can build high performance integrated circuits. Yes, that was the thought that everyone had like years ago, but we now realize that standalone graphene technology is not enough. There are several issues. So there's a proposal that you can combine these devices with CMOS platforms, because graphene is compatible with processing and integration of these CMOS processes. In this way, we can overcome issues such as switching and voltage swing that cannot be provided by the graphene transistors due to the lack of band gap in these devices. And then you can propose an hybrid graphene silicon CMOS integrated circuit technology, in which the graphene circuit here is built over a CMOS platform. So, but for this, you need compact models. For the CMOS part, we have 70 years of research. So compact models are there in constant development, of course, but they are available industrially. However, for the graphene circuit, for the graphene FET, there are still lack of compact models with high accuracy and low complexity. And you will need these compact models if you want to realize this hybrid technology.
5 minutes more, please, Aníbal. 5 minutes more.
Perfect, thank you. At the UAB, at the Universitat Autònoma de Barcelona, we have a simulation tool, which consists of experimentally calibrated numerical and compact models. And as you can see here, it is modular. I go quickly step by step. We have a module for the DC analysis. We have a module for transient, for AC, and for noise analysis. In each of these modules, there are several effects taken into account. So, for example, we have traps, we have noise, we have small signal and large signal and medium at high frequency. And yeah, basically, we are trying to develop, or we are in constant development of this tool. I brought you some examples. For example, how do we model the traps, but I gave this talk last year. I quickly give it here. So basically, you cannot avoid traps in these emerging technologies in which you use high permittivity oxides. So you need to consider this phenomena of trapping and detrapping, and you can include it into your compact model, for example, and you can reproduce then trap-affected transfer characteristics and trap-reduced transfer characteristics, as it is shown here and written here in this paper. You can also provide performance projections based on the trap performance. And this module, for example, is important for technology evaluation and for early applications, because you are gonna use you are gonna be affected by traps all the time, so you need to take this into account. As a second example, from a circular approach, we have, for example, this GFET-based mixer provided by our partners in Chalmers University in Sweden, and we applied a large signal compact model developed by Fran Pasadas. And also we built the same circuit that they tested here in our circuit design software. And we can see here the results. The first plot is related to the device performance, and we can see that at the direct point in which this application, the mixers, is developed, you will have a good calibration between experimental and modeling results. And we can provide here at a circuit level also good accuracy between experimental results given by the blue circles and modeling results here provided by the lines. This model-enabled circuit design is useful for technology benchmarking and optimizations towards high-frequency applications, for example. That's important for us. Well, I'm not going into the details, but I wanted also to tell you that we have already available a bias-dependent high-frequency noise model in our simulation tool, in which these results have been presented like 3 months back. We have measured, with the help of our colleagues in Dresden, the noise figures of merit. In this case, I show you the noise resistance. We built a compact model for this kind of noise with the corresponding equations, and we obtained a good fit between our compact model of noise and the measurements of the different figures of merit. This compact model actually is the first one including both velocity saturation effects and considering the degenerate nature of graphene. It has not been done before, and we have presented here in this paper. And these results are useful guidelines for low noise circuit design. If you want to build an RF low noise amplifier, you can go to these plots and see in which region, in which bias region your noise is minimum, so you can target that bias range in your application. If you have reliable and practical device models, you as a device model engineer, you are happy. But circuit designers are more happy because they can build amplifiers, mixers, multipliers, oscillators, modulators, whatever they think. They can even propose RF5G systems just based on graphene or emerging technologies. For this, as I said, we need a collaborative research framework. Just to finish, here, two-dimensional devices. So we have developed, or Fran also have developed in our group, a large signal compact model for two-dimensional devices. In this case, it was a molybdenum disulfide transistor, and we were able also to reproduce the high-frequency performance of this device. And also, in a collaboration with Instituto Politécnico Nacional in Mexico, we have developed a small signal compact model for black phosphorus transistors. And basically, we obtain or we reproduce the performance of 3 different technologies and build amplifiers, RF amplifiers at 2.4 gigahertz. And we can see, of course, the performance of what we can get with these transistors that were built somewhere else. And here we have published these results at the beginning of this year, and we obtained the first results of an RF amplifier based on BP FETs, and we see that we obtained around 11 dBs, and an error response, which is also important. We can think about the application later, but we have seen that this can be useful for the Internet of Things devices, for example. Other emerging devices in which we are working on, for example, diodes, RF switches, and interconnects based on one-dimensional or two-dimensional materials are not shown here, but you can ask me or contact me if you're interested after this presentation. And basically, just to finish, to give a wink to the title of this presentation, the importance of the compact, I want to tell you that the truth the experimental truth is rarely poor and never simple. You need a compact model for this, and I'm taking this from The Importance of Being Earnest, from Oscar Wilde, of course. And just to wrap up, I hope I gave you the message of the importance of the device modeling. We have seen the different modeling approaches and when to use it. Provide you a definition, my own definition of a compact model. What is it required for the industry? And I just present you some examples of the research we are doing in which I'm involved. And if you, as a student or researcher, are interested on a collaboration, just drop me a line. Yeah, I'm always open for this. And again, just thank you.
Thank you so much, Aníbal, for this pretty interesting presentation. Now we're going to ask some questions. I begin. Can we go to slide 32, please? Perfect. First of all, this is a general question mainly devoted to the students, to our youngest audience in this day. Regarding models for GFETs or other 2D nanostructure materials, there is a possibility to develop a universal compact model for this kind of 2D FETs. Yes or no, and why?
I mean, you mean the TMD FETs?
2D, two-dimensional.
2D. I'm sorry. Yeah, well, yeah. I mean, the intention is to be universal because basically you can have any two-dimensional material here and just change some parameters, such as, for example, the mobility, which is included in the equations of this equivalent circuit, and then just get the response out of it. We have tested, or Frank has tested this compact model only with molybdenum disulfide, but of course we are moving on trying it in different technologies. But yeah, the goal is to be universal and just for different 2D devices by just changing some material parameters. Of course, the mobility would not be the same in molybdenum disulfide than in black phosphorus. Yeah, the graphene is a special case, yeah, because it is a semi-metal, not a semiconductor like this one. That's the reason why it is presented and you know, it is studied differently than these ones.
Okay, excellent, thank you. There is a couple of questions. First of all, Reydezel Torres asks, first of all, thank you for the interesting presentation, Professor Pacheco. The food analogy was nice. Anyway, is it possible incorporating device aging into a compact model?
Thank you. Yeah, totally. So, for example, yeah, with this slide here. In this slide, for example, in the compact model, there is a parameter CIT. CIT means the charge due to interface traps. And this is one approach to model this effect. So basically, if you have an external effect to the intrinsic device, you can either add it here or add an adjunct network, such as the one presented by Chhandak. So if you want to include aging effects, of course, you can include it here in the charge formulation or in an adjunct network of your compact model. However, I should say that aging effects are still a long goal for these devices because the technology is still not there. We need to improve the yield. And after we improve the yield and we are sure that we can reproduce device by device, then you can incorporate these aging effects. Of course, there are already some proposals, and if I remember correctly, the group from Bordeux already proposed something for this. I don't remember the technology, but it was a 2D FET technology. Yeah, I mean, we can study that, but first we need to, together with the technology platform, improve the yield.
Okay, excellent. Thank you. Next question from Abel García. Which software is used for simulations?
You can use any kind of software. I mean, the commercial one, in any kind of circuit design simulation software. The commercial one is provided by Keysight, and it is called ADS, Advanced Design System. I mean, I can recommend you also another one, which is freely available. It's a free software, which is called QUCS, QUCS. And in there, you can incorporate also your compact models or use the ones that are implemented there. But I mean, if we're talking about emerging devices, of course, I recommend to build your own compact model. But yeah, I would recommend ADS, I mean, from the standard industrial point of view, and QUCS for the research and widely available point of view.
Excellent, thank you. Next question from Luis Manuel Rodriguez. Is this compact model applicable to GFET's technology from another fabrication group?
Yes. Let me see. So, for example, I mean, yeah, definitely. I mean, if not, it doesn't make sense at all to build it. I mean, of course, you can build a compact model for a specific technology, but it's useless if it doesn't work in other technology. Yes, this compact model is somehow universal because, for example, in this case, for the model of noise, we are using devices which were built in Lille, in France. You can see like the good response here. And in the case of the mixer here, the technology is different. The technology is coming from another lab in Sweden. So we have tested this model with technologies coming from different research labs and industrial labs. We are at the moment in which we can provide compact models for industry. Yeah, so for any kind of technology, of course, you change some parameters according to the requirements of the technology and so on. But yeah, you can say that our tool is universal.
Okay. Excellent, thank you. Next question from Eduardo Lugo. First of all, thanks for your presentation. He says, personally, I'm working in modeling of solid mounted resonators at harsh environments. And sometimes I have to suppose a lot of things because the fabrication group and the modeling group do not speak regularly. So have some devices to solve it, or at least get improvements in terms of communication to integrate the whole work? I mean, I think Eduardo wants to know if communication between modeling group and fabrication group, it is important or not.
It is quite important. It's the importance of being earnest. So basically, that's the main motivation of my talk, because as you said, sometimes we are not talking to each other, yeah. And I have seen it in different environments. The only way that a technology would work is if we speak with each other without prejudice. I mean, for example, the technology platform, they always want to fabricate and measure, and that's it. Yeah, but that's not enough. The device modeling, of course, we always want to understand the physics and provide the really sophisticated models. But if they are really sophisticated, then maybe that you cannot build circuits with it. So you need to know also the requirements by the circuit design group. So you need a constant feedback. And of course, yeah, I have faced these similar problems when working with carbon nanotube FETs or with graphene devices. That's what I said at the beginning. This kind of collaboration is granted already it's taken as granted in incumbent technologies such as silicon germanium devices, 3.5 and so on, but it is missing in emerging technologies. So I really strongly suggest to collaborate all the groups involved in any emerging technology.
Okay, thank you. There is a couple of questions, one from Eusebio Patiño and the other from Marta Galaz. With Eusebio Patiño, we can talk later. I will read the question from Marta Galaz. Congratulations for this great talk. What kind of method did you use to perform the noise characterization of your devices? Why you are limited to 1 gigahertz for noise characterization?
Thank you, Marta and Mauro, I suppose, as well. Wait, type with me a little bit. Yeah, that's quite interesting. So basically, we use the Y function factor, the Y factor method, sorry, to measure these devices. And we are limited to 1 gigahertz because of the gain. So these devices, the cutoff frequency of these devices we were testing is around 2 or 3 gigahertz. So the measurement setup for the noise characterization requires higher gain at these kind of frequencies. So it was a huge challenge to obtain these noise figures of merit here. Because, you know, if you don't have, if your gain is minimum, then the measurement setup cannot solve the equation to give you the noise figures of merit. So we have to be really careful. And actually, we wanted a bias-dependent high-frequency noise model, not only for 1 gigahertz, we wanted to go further or lower. But anyway, that was the best frequency for us to obtain the high-frequency the noise figures of merit. Yeah, we are limited by the equipment, not by the equipment, by the devices. But I have to mention that there is another approach to obtain these noise figures of merit, and which is called Y50, and we have seen that. And in contrast to us, they provided the high frequency noise characterization and model for different frequencies, but not for different bias. So yeah, we are complementary each other.
Excellent. Yes, and finally, I am Mauro. It's really a pleasure to have this nice talk. Thank you.
Thank you.
Will you share, please, your contact information, says Moises Sanchez?
Sure, definitely, whenever you want. Yeah, they're just there, Aníbal.Pacheco. You can Google me, and yeah, that you can contact me in different social networks whenever you want. And as I said, yeah, I'm interested in collaborations as the ones we already have with IPN. Yeah, drop me a line.
Thank you. Thanks a lot. Okay, we have already finished, and I will present your diploma. Aníbal, can you stop sharing?
Thank you.
Thank you. Well, who can share all opponents? Okay. Perfect. Yes. The Instituto Politécnico Nacional and the Eugenio Méndez Docurro chair present the certificate of participation to Aníbal Pacheco-Sánchez for his participation on the webinar Terahertz applications based on emergent and high performance electronic devices, part 1, with the conference, The Importance of Being Compact, Modeling Two-Dimensional Devices Toward RF Applications. Thank you a lot, Aníbal. And finally, I would like to invite our audience to the talk, Digital Bridge, which will begin in a few minutes. You can follow us in Twitter, and you can find the flyer from this talk. So you will be welcome in this talk. Thank you so much. We will see you tomorrow with the last 3 talks of this webinar series from Terahertz Electronics. Thank you so much and have a nice day.
Thank you. See you.
See you tomorrow.